Good evening, everyone, and welcome. We appreciate you joining us tonight. My name is Sam Adams-Lanham. I'm the Community Engagement Librarian at the Barrington Area Library. So that means I do programs for the benefit of our local nonprofits and alongside our local nonprofits. And tonight I'm collaborating with actually one of the first people I ever collaborated with when I stepped into this program, and that is Jennifer Lucas of Go Green Barrington. So I'm going to turn things over to Jennifer to tell you a little bit more about Go Green and to introduce John. Thank you.
Good evening, everybody. As Sam said, my name's Jennifer Lucas, and I represent Go Green Barrington. And we're excited to partner with the Barrington Area Library tonight to bring you this program. Go Green puts on educational programs like this, some other projects, things like highway cleanups. And I put my email address in the chat, so please send me a message if you'd like to receive our newsletter. And our speaker tonight is John Scott. I heard John a few years ago, maybe 4 or 5 years ago, as part of a panel of experts. And the information stuck with me ever since. I was constantly referring to the information he shared. So I was extra excited when he agreed to join us tonight. So John is a senior chemist at the Illinois Sustainable Technology Center at the University of Illinois. He has degrees in chemistry and environmental health. He's been studying legacy and emerging contaminants in the environment for the past 20 years, publishing dozens of research papers along the way. John's research interests include emerging contaminants such as microplastics and Pfas, waste utilization, and natural products. We are lucky to have the chance to learn from John tonight. I hope each of you will share what you learn with somebody else after tonight. So welcome, John Scott. Please proceed.
Thank you very much for that nice introduction. And I am going to, okay. Since the emergence of mass-produced plastics around the 1950s, our global appetite for these materials has been increasing at a very rapid rate.
John?
And yes.
Sam, before John gets started any further, is everyone, I'm seeing the Barrington Area Library's website rather than John's program.
Okay, thanks for letting me know. It must be the way I'm sharing my screen. Boy, I'm glad you caught me right up front.
I was loud and noisy. There you go.
Is that better?
Yep, that's perfect.
Thank you. So since the emergence of mass-produced plastics in the 1950s, our appetite for these materials has been increasing at a very rapid rate. And here on the left, you can see a chart that shows that back in 2013, we were making about 320 million metric tons of this material every year. And what I find astonishing is if we continue down this path of business as usual, actually, it's estimated that by the year 2050, every year, we will be cranking out 1 billion metric tons of plastic. So just incredible amount of material. In fact, back in 2017, it was estimated to date that we had already made 8.3 billion metric tons of plastic. So every time you make this much of a material, you have to ask yourself, well, where's it going? So at that time back in 2017, it was estimated that we were sitting on about 6.3 billion metric tons of plastic waste. And here's a pie diagram that shows you where the vast majority of this material goes. Small percentage is incinerated, about 12%, and that in itself has issues like hazardous air pollutants and so on. But only a small percentage is recycled, 9%. Even saying it's recycled is a bit of a misnomer because there's only so many times before you can recycle a plastic before it's landfilled. So the vast majority of these materials, 79%, find their way into the landfills or become fugitive in our environment. So as a result of this, plastic is basically ubiquitous in the environment. Okay. Oh, I went too far. There we go. So let's talk about some definitions. So when I refer to things as macroplastics, typically we're referring to things that are greater than 5 millimeters in size. Microplastics, by definition, is the plastics that are in the size range of 5 millimeters to 1 micron, or 0.001 millimeters. So that's what we term microplastics. And now we hear a lot about nanoplastics. In my opinion, nanoplastics are materials that are less than 1 micron, but the lower end of nano is kind of nebulous right now, and nobody can really decide if it's 10 or 100 nanometers. But here's a little diagram on the bottom that kind of gives you the scale of these things. And as you can see, as we get smaller and smaller sizes, they become more and more troublesome because they migrate in the environment more, and they have the potential to cross biological membranes, especially in the nanometer range. And the other thing is these materials are very complex. There's thousands of polymers out there. So it makes it a lot more difficult to tackle this problem. So there's two classes. The first are called primary microplastics, and those are the ones that are intentionally made to be very small. And these are things like the microbeads they used to put in the cosmetics and our toothpaste, and also nurdles, which is like a base material for when they make a larger plastic. And then sometimes they use plastics and industrial abrasives. And you know, we used to find a lot of these primary microplastics in the environment, but thankfully, back in 2014, they had the Microbeads Free Waters Act, and actually it seemed to be quite effective because we don't find as many of these materials in the environment anymore. But what we do find is what I believe are from the result of secondary microplastics. And these are things that are breaking down from a larger material. Large plastics over time just break down to smaller and smaller pieces due to wear, abrasion, ultraviolet light, even some micro or biodegradation. So where do we find microplastics? Basically everywhere we look. Surface waters have been intensively studied. We find them in almost just about every water we look at, but also sediments and soils. We believe that that's a final sink for a lot of these materials, and even indoor air and dust. Indoor air is actually quite a known significant route of exposure to humans because we surround ourselves with these textiles and the carpeting and all those microfibers in the air. But we find it in our food and our beverages. We intentionally used to add it to cosmetics. Wastewater is a common source for microplastics, and I'm going to talk more about that later on. We've all seen the pictures of birds cut open and cigarette lighters and all kinds of plastic materials in their bellies, and fish as well. And actually our group was the first people to report microplastics in karst groundwaters. So karst groundwaters are these open porous systems. They have sinkholes, they're cavernous type. Here's an example down here of the sampling team sampling in the karst groundwater. And it's not surprising that we find microplastics in there because they're so open and porous. But the significance of that is 25% of the world's population gets their drinking water from karst sources. So it's a pretty significant, source to find microplastics here. And we're even, just a couple of weeks ago, we started to see reports of microplastics showing up in people's lungs and even in their blood. So the bottom line is everywhere we look, we seem to find microplastics. And that's why we say they're ubiquitous in the environment. So the question is, well, should we be concerned? And I think that one of the things that are most alarming about these materials is the sheer persistence of them. So here's some examples of how long it takes for some common materials to break down in your cigarette butts and your plastic bags, anywhere from 5 to 20 years. And in the realm of persistent pollutants, that's a pretty long time. But now let's talk about things like plastic straws, disposable diapers, plastic bottles, up to 450 years to break down. It's incredible. A child uses something like 7,000 diapers until they're potty trained. And those diapers are going to be around more than 5 times that child's life expectancy. So our landfills just must be swelling with these plastics that are just taking forever to break down. But beyond the fact of persistence, we also know that we add a lot of things, a lot of additives to plastics. Over 6,000 chemical additives are known to be used by the plastic manufacturing. And here's some examples up here of some beach plastics that I analyzed on the right, upper right. And you can see this green fragment, 1.4% lead. And I believe that's a piece of a garden hose. So don't drink from your garden hose, and don't let your dog drink from your garden hose. But anyhow, here's another example. This is what I believe to be like a Mardi Gras bead, 1.2% antimony. I also found chromium and cadmium in the sample. But beyond even metals, we know that we add thousands of organic additives, things like phthalates, which make PVC flexible. Bisphenol A is quite notorious because it was turning up in baby bottles for a while, but it's an antioxidant and it's also used as a base material for larger polymers. But we also have things like plasticizers like triphenyl phosphate, flame retardants like the brominated diphenyl ethers, and thousands of other compounds. And many of these compounds we know are extremely persistent. We know they bioaccumulate, so they concentrate in organisms more than the surrounding environment. But they also, many of them are known or suspected to be endocrine disrupting, so they interfere with the hormones in our body. So the other thing too about additives is they seem to turn up in places where they shouldn't. So the plastic manufacturing industry is regulated. There's a limit to what they can add to a plastic depending on its intended final use. However, you always hear about maybe lead or flame retardant showing up in a child's sippy cup, and that's not intentional. We believe that happens through mismanagement or recycling. Originally a material was intended for one use, but through recycling, it found its way into something that would become in contact with humans. And electronic waste is another example we believe is carrying a lot of the additives into the recycling streams. So even beyond additives, we know that plastic will absorb environmental pollutants. And you can think of them as little sponges in the environment that will soak up anything that's nearby. And I'm going to show you an example of a study that I did a couple of years back to look at this. But we see them absorb all things like PCBs and these legacy pollutants and polyaromatic hydrocarbons, and even some of the newer emerging contaminants we find associated with plastics. And I've even found things like algal toxins and pharmaceuticals, personal care products, even hormones. And as these things get smaller and smaller and smaller, they have more surface area, which gives them a higher capacity to absorb things. But besides being a vector for chemical pollutants, plastics can also absorb biological materials. And my colleagues at Loyola University Chicago have done a lot of work to show that the microbes that grow on plastics are a lot different. The diversity of them is much different than the surrounding environment. So they basically breed exotic bacteria and biological materials. And in some of my studies, I've also found that this biofilm that grows on the plastic also enhances its ability to absorb chemicals from the environment. And in addition, it also influences how they move through the environment. A plastic that might normally float will grow a biofilm on it and then sink and so on. So let's see. So one of the questions is then, do we know if there's adverse effects to human health or negative impacts to ecosystems? And we really don't know. The jury's still out on this. There are studies, but many of them are conflicting. And this is really an area ripe for research. But the point is that when we talk about it, we need to talk more than just plastic. We need to talk about the additives, the stuff it absorbs from the environment, the biological materials, all the other stuff that associates with plastic. And that's what's so challenging about this microplastics and plastic pollution. It's a lot different than the contaminants that we had encountered in the past, because before it would just be some class of dissolved chemicals. But I believe that microplastics interact with the environment more, and they're a lot more complicated because there's just thousands and thousands of polymers and copolymers out there. So about 7 years is when I got into the whole microplastics thing. And it was some colleagues of mine were picking out little pieces of plastic from sewage sludge. And my laboratory has a very unique capability called pyrolysis mass spectroscopy. And it's well suited to identify all these little pieces of plastic. And that's how I got roped into this microplastics thing. But ever since then, we've kind of blossomed in my lab into all different areas. We looked at additives, we look at contaminants in plastics. In fact, my group was the first with some partners in the United Kingdom, where we specifically looked for things like rare earth elements in common plastics. And we found them. Surprisingly, we found them. And we think it's because of recycling in electronic waste finding its way into these recycling streams. But we've also done things like look at how microplastics will absorb environmental pollutants. We look at how they move through the environment. We look at how they weather and degrade in the environment. And down here, these blue images are from a study that we did of a cargo spill in the Atlantic of printer cartridges that were showing up all around the Atlantic Ocean, from Norway to the Canaries to Florida. And people were sending into my laboratory, and we were studying how they degrade over time. And what we found is that, a lot of the additives they add enhance the ability of these things to break down. We also developed methods for analyzing microplastics, which I'm going to talk about in a minute here. And then we also look at, things like, microplastics and environmental samples and how they occur. But this last thing we're not really interested in anymore, because it's like, why go out and collect another water sample and analyze for microplastics? We're going to find it. So now we're trying to focus our attention on solving the problem instead of identifying the problem, because we know it's out there. So first, let's talk about how do you analyze these things? And that's really difficult. These are very different than what we did in the past. But back in 2015, the National Oceanic and Atmospheric Agency, or NOAA, they actually developed a pretty good method. It had all the right parts to analyze for microplastics. And it basically involves doing a wet sieve. So you run your water. We're going to use a water sample, for example. That's the easiest way to explain this. But you pass it through like a filter. And then the filter size they used was 300 micron. And then you digest it to remove all the organic matter. And then you separate it in a salt solution. So you make all the plastics float to the top, and all the sand and all the heavy stuff float to the bottom. And then you can capture it on a filter and analyze it under a microscope. So when we looked at this method, we saw, hey, this is a pretty good method, but we thought we could do a better job. And the two things that we looked at and we focused on was this initial fractionation of the microplastics. We thought that 300 was just way too large. But we also looked at a better job of how we could float these things. And this is an example of some of the equipment that we fabricated in our lab. These are density separators. So when we pour a salt solution in here and we put the sample and make the plastic float to the top. So size is extremely important. In fact, if you were following, this is some example of some data from stream sediments collected up in Iowa near agricultural sites. And you can see at the bottom, the x-axis, this is the area of the microplastics we find. And the y-axis is the percentage of the counts, the total counts. And as you can see in both these graphs, as you go to smaller and smaller size, these things are occurring more and more frequently. And in fact, if you're following the NOAA method, you wouldn't even pick up most of this stuff. In fact, the smallest unit, the thing I tell people is we can see about 20 by 20 micron. 400 would be the area here. And that's our cutoff. But you can see that as you go down, these things just drastically increase. And we see two different types of curves. It's kind of interesting. This one's the one on the left is a very slow, gradual increase as we go down in size. And then the one on the right just kind of skyrockets. And we don't know yet. We're still working our way through this project. We'll be done in about 3 more months. But once we have all the data, we can start to try to figure out how to explain this. But definitely size is important. And that's what you have to ask yourself when you see these studies. Because like I said, a lot of people are only looking maybe down to 10,000. And look at if that was their lowest limit, then they would be missing all this other stuff. The other thing we need to talk about is the density. And most people in the past were using a saturated sodium chloride solution. And that only gets you to a density of about 1.2. However, that's great for things like polypropylene, polyethylene, or polystyrene. But you would be missing things like polyvinyl chloride, which is the 3rd most produced plastic in the world. Or you'd be missing polyesters because people are interested in polyesters because we believe they shed a lot when you do your laundry. So we played around with a bunch of salt solutions. We like this potassium iodine. It gets us to about 1.7. Obviously, it won't get things like Teflon, but it'll cover most other materials. I even have my special sauce, which is a mixture. I can't tell you about it, but it's a secret. But it does get you to a density of about 2.3. And I only use that in special cases because, for instance, if I was to use that for a sediment, I'd be worried about starting to float heavy stuff and accidentally counting that as a piece of plastic. So the density is very important, and we have to consider that when we're analyzing our samples. So just to show our improvements, we were able to push our detection limit to 20 by 20 micron. We're actually starting to go even lower. We're developing methods in-house right now to do nanoplastics. But right now, for the bulk of the work that we're doing, this is our lowest detection limit. And also we were able to achieve a much greater density separation. And that's why I believe a lot of our work, we find a lot more microplastics, because a lot of people were missing these things just because of the way they were preparing them. Okay. Oh yeah, let's talk about how we even report microplastics. And this is a major flaw. So, and you look at the studies and what people are reporting, you'll see this unit, particles of plastic per liter of water. And it's really a meaningless unit. It doesn't do anybody any good. It's not a number anybody can work with. And you can think about it, if we go out in the environment and we collect a sample and it has a particle, microplastic in it that's 500 microns in length. Well, by the time we take it back to the lab and do all of our magic, we might actually break that piece of plastic into 10 particles that are 50 micron in length, right? So really, we can't even compare data within studies when we use this type of unit. And we know the vast majority of the plastic we find is highly weathered and it breaks down very easy. So our approach is to do very, very detailed size measurements. And when we do that, we can make some estimates to the mass of the plastic we find. And this is a number that people can work with. Things like the toxicologists, the modelers, the chemist, everybody, they need, in the past, we've always expressed contaminants in micrograms per liter or milligrams per liter or milligrams per kilogram. And these examples here are actually quite crude. We use sophisticated software that gives us very, very detailed area measurements. And we know this isn't perfect, but we know it's a step in the right direction. And actually, I tell people that my estimated masses are actually quite conservative, but it'll give you a lower bounds of really what's in the environment. And this is a perfect example of this. So these are two different sets of data. The ones on the left were collected up by you guys up in McHenry County. And you can see that if we look at it in terms of particles per liter, I mean, some of these samples, 200 particles per liter. And then here's another set on the right from Tennessee, and they were only like 18 particles per liter. So when you look at this data, you say, wow, the one on the left, there's a lot more plastic in those surface waters than there is of the ones on the right. But when we look at it in terms of mass, they're really quite similar. You can see up in the left, 14 micrograms per liter. In the Tennessee, the highest one is 16. So what that means is the ones in McHenry County were much smaller. So they were more numerous, but also much smaller. And in terms of it in total mass, they were quite similar. So we have to look at both those things. And the size and the mass estimate is very, very important. So moving from that, I want to talk about a study that we did a couple of years ago up in Lake Muskegon, Michigan. And here what we did is we wanted to see to what extent do plastic absorb environmental pollutants. So we made, I know it's terrible, here I am saying microplastics are bad and I'm making them, but we made 3 different types of microplastics. We made polypropylene, polyethylene, and polyester. And we built these deployment units and we deployed them at 2 places within Lake Muskegon, one in the middle of the lake and then one in the channel. And this channel interacts with Lake Michigan. And this is very unique than most studies because a lot of studies would go out and just scoop some plastic from the environment, but they didn't know what type it was. They didn't know how long it was there. They didn't know if it moved around. So we wanted to get a more controlled study, and that's what we achieved here. So I can't go into all the details because this would be a 2-hour talk in itself, and I'm only going to give you some of the highlights. But we looked at 85 different persistent organic pollutants. And we looked at things like polychlorinated biphenyls, which have been banned for a long time, but we still find them in the environment. We also looked at polyaromatic hydrocarbons, which are carcinogenic. They're usually produced from combustion, but they're also associated with things like oil and coal. We looked at chlorinated pesticides and even DDT. DDT has been banned for so long, but just like plastic, we find it everywhere. We looked at organic phosphate esters because they're plasticizers. We looked at flame retardants, Whoa. And we looked at this new class of perfluoroalkylated substances, which are fluorinated compounds, which I believe are a lot like plastics in that they're very persistent, they're very ubiquitous, they're kind of like surfactants, and they're quite different than the other chemicals that we looked at. So the first thing we had to do is we had to look at how much contaminant was in the water. And I've kind of summed these into classes. And you can see that the polyaromatic hydrocarbons, the blue bar here, was the highest of all of our target compounds. But when I say high, that's relative. These units are micrograms per liter or parts per billion. So really, we only saw about 120 parts per trillion at the highest. And unfortunately, it looks like Pfas didn't make it to my chart here, but Pfas was down here about 2 to 5 parts per trillion, which is common for surface waters. So this serves as our background concentration. So you can see here's the PCBs here, DDTs, 12 parts per trillion, and even some long band chlorinated pesticides. So this is the water samples that were collected when we deployed. Now this is the PAHs associated with the plastics. And this is the site in the middle of the lake. And you can see that the top bar, the blue solid bar, is after 1 month. And then the light blue bar is after 3 months. And even within this short amount of time, we're concentrating PAHs hundreds of times the background concentration, okay? And the other one I want to show you is the PCBs. It's really interesting because it seems that polyethylene really absorbed a lot of PCBs. And it was only within the first month, and then it kind of dropped back down. Polypropylene a little bit, and polyester not so much, but definitely not what we expected. We wanted to try to figure out, well, what the heck is going on here? This is really odd. So what we did is we looked at the profile of PCBs, and there's about 209 different types of PCBs that are out there. You can think of them as the Legos of chemistry. But we found one certain PCB was the predominant, was the reason we saw so much, and it was this dichloro PCB. And it was really surprising. We have no explanation for this right now, but it's a lot different than what the PCB profile would be in the environment. And for some reason, this thing just concentrated. And I have theories about it, but we would have to really go back and do some more studies to figure out why. But very interesting result and not expected. I want to talk about Pfas. So we did see a lot of trends with the other pollutants. But what we saw with PFAS is it really didn't seem to matter what type of material. It didn't really seem to matter where it was in the lake. We just kind of almost seen this consistent amount of absorption. And we thought this was very strange. And PFAS is, like I said, they're a lot different than the other chemicals we looked at chemically. So we wondered if it had to do with the biological materials that grow on the microplastics. And here are two. Here's on the top is the virgin plastic that we started with. And after 3 months, you can see it got that slimy biofilm on it. We thought, wow, maybe the PFAS is actually interacting with the biofilm. So what we did is we took some virgin plastic, we exposed it to PFAS in the laboratory with no biological materials, and we see a very, very low amount of absorption, only 15 to maybe 28%. So there's something special about the plastic in the environment that really enhances the ability of these things to soak up pollutants. So the key findings, PAH is up to 280 times background concentration. PCB spiked and then came back down, but they went all the way to 380 times. Pfas about 260. So overall, the degree of absorption seemed to be that polyethylene absorbed the most, followed by polypropylene and polyester, except for the case of Pfas. We did see big differences even within the water column. There were some places where we deployed 1 at 2 meters in the water column and then at the bottom. And even within that same site, we saw drastic differences. So really, one of the things that we were surprised about was the microplastic absorption is also influenced by other materials. I think it has a lot to do with biofilm, but it could be things like, metals precipitating on the plastic and interacting with the pollutants, or potentially natural organic matter. But I really think it has a lot to do with biofilm, and we would have to do more studies to confirm that. So when I got all this data, I got all excited and I sat down and I wanted to try to figure out, how much does this add to the body burden of an organism that would come along and eat it? And what I found is that I believe it would take a lot of microplastic. A fish would have to eat an incredible amount to really increase its body burden as compared to what it's being exposed to in the water or the sediment or its prey. But I have to throw out some caveats that these were short time exposures. 3 months was the longest time we exposed it. We wanted to go longer, but we had problems with overwintering in the lake. When it froze, we weren't able to deploy. And we know that about 50% of all the plastic that we find out there is about 14 years or older. So really the time scale is very short. Also, our materials are quite large, 1 to 4 millimeter in diameter. And we know that the microplastics that we find in the environment are much smaller. Smaller size means more surface area, means more ability to absorb contaminants. And the other thing is our materials were virgin, we made them. But really we know the stuff we find in the environment's very aged, very weathered, also gives it more surface area and changes the surface chemistry and allows it to absorb pollutants much differently. But the other thing too is we're neglecting additives. So remember I was talking about all the additives and we know that they're there at concentrations magnitudes higher than what they're absorbing from the environment. So we have to take that into account too. And the bottom line is we just need to consider more than plastic alone with regards to ecosystems and human health. I know I sound like a broken record on that one. Okay, let's talk about another study we have ongoing right now. We're about halfway through. And one of the things that we asked ourselves one day is, where do we think the biggest sources of microplastic pollution to the environment? Where are the biggest sources to these things? And then in the beginning, I told you that about 79% of all plastic is destined for the landfill. So that would be a logical place to start. And I don't think that when plastic finds its way in its landfill, the story ends there. Landfills are aggressive conditions. They have high temperatures. They're designed to break things down. They have high microbial activity. And I believe what happens is all this plastic that lands in the landfill is getting broken down to smaller and smaller sizes. And then it translocates into what we call the landfill leachate. Now in 1991, prior to that, landfills weren't required to be lined. But after that, landfills were required to be lined. And what happens is that leachate that's collected from most of these lined landfills is actually sent to a wastewater treatment plant. Excuse me. So a wastewater treatment plant is not designed to deal with plastic. So the only two places it really has to go is either the biosolids or the wastewater effluent. It's directly discharged to the environment through the effluent. If it's in the biosolids, then typically here in the Midwest, the vast majority of our biosolids we then land apply to our agricultural crops, where then the plastic has the potential to run off to the surface water, to run off into surface waters. It has the potential to get in our groundwaters. And over time, as it gets smaller and smaller, it has the potential to be taken up by plants. So these are the systems that we're studying right now. And we also know that there's a great deal of plastic coming in the wastewater influent. But the wastewater influent is an incredibly large volume of water. A lot of the plants that I work with are about 10,000 gallons per minute. There's no way you're going to be able to address the micro here. But leachate, that's a different story. Some of the plants I work with, they take about 2,000 gallons per day. Other ones are taking about 33,000 gallons a day, but that's a volume we can manage. So if my theory is correct, then we could potentially treat the microplastic problem here and then hopefully reduce how much is being emitted to the environment. Now, obviously, the best place to treat it is right here. Let's not put plastic in the landfill in the first place. But even having said that, if we come up with a new material tomorrow and all of a sudden all plastic production stops, we still have hundreds of these systems in Illinois alone that will be slowly diffusing plastic for decades to come. So it'll be a legacy problem that I believe is the importance of these systems. And I think that's why we need to study them. Let me show you some data. So this is one of my sites. I'm going to call it System X. And this is a landfill that's actually been inactive for 30 years. It's unlined. It's about 90 acres. And it has about estimated to be about 8 million cubic yards of waste. And the way this system works is there's actually a couple of leachate pumps, and they pump the water, the leachate that comes out of the landfill into the wastewater distribution system. So this is one of the sampling points that we looked at. And we also sampled here at the influent to the wastewater treatment plant. We sampled at the effluent of the wastewater treatment plant, and we sampled the biosolids that came out of the system. And you can see that it looks like about 2.6 micrograms per liter in the leachate, and it's about a factor of 10 greater in the wastewater coming into the wastewater treatment plant. So the vast majority of plastics entering the system is through industrial and residential wastewater. They have no storm drainage. But you can see that the vast majority of microplastics going out of the system are indeed in the biosolids, which then are land applied. So this is a small amount in the effluent. But having said that, effluents are large volumes. There's probably, I don't know the exact number, but I'm willing to bet you somewhere around 10,000 gallons per minute being discharged out to the local stream. So really that is a significant amount. But 99.9% of all plastic seems to, in the system, to go to the biosolids. So what else can I say about this system? However, you look at this number and you do think it's pretty low, but we believe what's happening is a lot of the plastic in the landfill might actually be getting caught up in the soil. You can kind of envision the soil as being a filter, but over time, they might break down to smaller and smaller sizes and then all of a sudden be released to the surrounding environment. So although it looks pretty low in this system, it's still concerning because they could still be becoming fugitive in the environment. And remember, this landfill has been closed it's been closed for 30 years. So chances are it doesn't really have as much plastic as compared to an active landfill. Within the last 20 years, we have produced 50% of all the plastic since 1950. So it's because of that rapid increasing rate that also we might be seeing this effect. Let's talk about System Y. System Y is a landfill it's still active to this day. It is lined. It's about the same size as my other one. And it has about 12 million cubic yards of waste. But in this system, all the leachate is collected to a storage tank. And then these big trucks come in and suck it out and then take it to a pre-treatment wastewater facility, okay? In this pre-treatment facility, there's a private company and they treat this stuff, and then whatever their effluent is, then they discharge it to the wastewater treatment plant. And you can see in this system, drastically higher concentrations of microplastics. And that's kind of what we expect because it's lined, we're capturing them all. But here again, as the microplastics move through the pre-treatment system, the vast majority of them partition to the biosolids. A little bit is actually discharged to the wastewater treatment plant. These biosolids are then, depending on the test results, they're either land applied or, and the interesting thing is sometimes they're sent, if they fail for certain parameters, they're actually sent back to the wastewater, to the landfill. And you can imagine that we're starting the cycle all over again, but breaking the plastic down to smaller and smaller pieces every time. So this is just some of the data, and we're halfway through. We have other study sites as well. I think we have 4 total, but we're going to go back. This is preliminary data from one trip, but now we're going back and we're repeating our sampling more and more because we know the concentrations will change over time, and we want to get more data so we can do statistics and further validate these findings. But hot off the press, nobody's seen this yet. So what are the key findings here? The concentrations of microplastics in the leachate of a lined landfill, so far what we've seen are 35 times higher than an unlined landfill. But having said that, you can say maybe unlined are not a concern, but there is a concern that, they are leaching, still diffusing microplastics to the groundwater and the surrounding sources. And then, the pre-treatments and the wastewater treatment processes accumulate microplastics in the biosolids. We know that from our study. Other people are reporting that too. It's a large amount, 99.9%. And the other thing too is we're starting to identify potential places to treat these things. But we don't think it's fair to point the finger at the wastewater treatment plant and say, hey, you have to solve this problem because they're just stretched so far with resources already. I mean, these guys are saints. In fact, next time you see a wastewater treatment plant operator, you should give them a hug. They're dealing with our waste every day, large volumes, so many more contaminants. So if we address the microplastic problem at the treatment facilities, we need to do so in a cost-effective way, and we cannot minimize their operations. Okay, it's not all gloom and doom. I hope I didn't depress you, but I think there's solutions to these problems. We created this problem. This is a local problem that we've created, and we can locally solve it. Unlike a lot of people, there's other people that are out in the Pacific on a little island that everyone's waste is flowing up on their shores, but not us. We've created it. So how are we going to fix it? In pollution prevention, we have something called the waste minimization hierarchy. And in this triangle, the top runs are the most preferred option for addressing pollution. And the top run is where we can all of you can really make a difference. Prevention, source reduction, producing less plastic, consuming less plastic, throwing away less plastic. This is the most efficient and the most cost-effective way to deal with this pollution. However, it's the most difficult. It requires things like materials, new materials. It requires behavior change. But really, this is where we should start addressing the problem. But we can also do things like reuse, repurpose, recycle. People say, oh, 9%, why do I even bother? Well, if you don't recycle it, it's got a 0% chance of getting recycled. So, and I really think that we really need some stimulation of innovation and technology in the area of recycling. In the past, our idea of recycling was just shipping the stuff off to China or shipping it off to Vietnam, and we called that recycling. But those countries aren't accepting these materials anymore. And I really hope that that stimulates us to really innovate in this area. In fact, I know the Department of Energy right now is looking for ways to better recycle thin films. Thin films are used a lot in packaging and food packaging. They're difficult to recycle because they're multi-layers of different materials, and they're really problematic. They're filling up our landfills. So I know that they're trying to stimulate innovations in that area. Beyond recycling, we have recovering value. This is things like trying to get energy from these materials. I'm not the biggest fan of this, but I have to entertain the idea. I kind of think of it as taking it from one environmental compartment and just, burning it or incinerating it and turning it into the atmosphere. But we have to entertain this idea. At ISTC, there's a whole group of people that are working on converting waste plastic to drop-in fuels. And it makes sense. A lot of plastic is made from petroleum products. So they're just depolymerizing it and then turning it into something that we could, put in our gas tanks. So, but, there's a lot of issues with that. Hazardous air pollutants. What about the additives and things like that? But at the same time, what do you do with these materials? Do you landfill them? I just told you that landfill is an issue. So, I mean, we're kind of stuck between this, what do you do with it? So that's why I kind of entertain these ideas of recovering energy and value from them. And obviously the last thing that we don't want to do is dispose of it. We don't want to put more in the landfill. I also believe that we really need an interdisciplinary approach to the plastic pollution problem. And these are some notes and ideas that I've jotted down, and just my personal thoughts of what needs to happen to reduce the environmental loading of plastic pollution. And I've kind of identified 4 major areas. In the upper left, I have an area called source appointment. This is finding the major sources of these things: landfills, roadways, is it textile washing? Let's identify where are the biggest ones and tackle those right away. And let's get a handle of how much plastic is out there. But also on the bottom here is fate and transport. How do these things move from the major sources? What are their final sinks? How do they break down? How do they change as they move through the environment? And then up here on the upper right, we have solutions. Obviously, source reduction, development of new materials. We need innovations in recycling and also packaging. Packaging is one of the largest users of plastic materials, and it's been exacerbated by COVID. Imagine how much more people are shipping stuff. And I mean, I don't know about you guys, but when I receive stuff at work, it's crazy how much plastic is in there for a little vial of some chemical. It's just incredible. And I think there are better ways to do this. But also we need to come up with technologies that are cost effective. I mean, you can have the best microplastic removal system, but if it's not cost effective, then nobody's going to adopt it. But also looking at things like social and economical aspects. And obviously in the bottom here on the right, education and outreach is so important. And that's why I do these talks. I'm an optimist. I think that if you give people the information and you let them know how they're impacting the environment, they will make better decisions. And I also believe that, we have to engage with stakeholders. We got to get municipalities involved. The scientific community needs to do a better job of getting their findings and their information out there. So I go to a lot of these contaminant conferences, and the physical sciences are really well represented. We have great toxicologists, we have great chemists, we have great geologists, hydrologists, ecologists. But what I am seeing lacking is the social sciences. I am hungry to find people in psychology and sociology that can change people's behavior. I mean, I think these people can make a really big difference. And even economists. People always tell me that, plastic is so widely used because it's so cheap. But is it? I think there's a lot of hidden costs with plastic. I believe that if somebody sat down and ran the numbers, they would find out in the long run that it actually might not be cost effective to use plastic because it sticks around for such a long time. It's so problematic, and because it's filling up our landfills. And, bringing in these other disciplines and working together with the common goal of reducing environmental loading of plastic, I think would really enhance our efforts. Wow, has it been an hour? But that's it. That's all I have, and I'd open it up for questions.
Okay. All right, thank you very much. I am going to, would you mind closing your screen share? And then I will bring myself back in for a spotlight. So got a couple of questions that I think are kind of the before and after part of the problem. So I'm going to start with the after part. For example, there's a medium range restaurant that my husband and I get carry out from frequently. And they used to have a place where you could put notes, and we'd always say, no utensils. And we still get utensils every time. Now they ask you when you place an order if you want utensils or not. And I say no. And we still get utensils. I tweeted their headquarters and was like, what the heck? And they're like, oh, training issue, we'll take care of it. I'm like, okay. So what suggestions do you have for those kinds of situations that where you're being asked, you've said, no, I don't want this. I brought my canvas bags in, don't give me a plastic bag. And they're like, oh, but this, these berries might fall out. I don't care. How do you handle those things?
Yeah, that's behavior change, stuff like that. I mean, I would save those materials. You could bring them back. A lot of times they won't take it though, because it's been contaminated maybe, or repurpose them, use them somewhere else if you can. I mean, that might be helpful on your end. Obviously problems that you can address are the easiest ones. But yeah, you can't completely avoid all plastic. I mean, but you got to try. Every little bit helps, right? I mean, it's daunting how much plastic is out there, but I'm kind of skirting around the question. I do think training would be helpful. And, I mean, for a business, you would think that there would be an incentive for them to do a better job of not giving that stuff out, because that's stuff that they're paying for, And it's just mind blowing to me when you tell a business that, hey, you could save money if you don't give this stuff out, then that you think that would incentivize it. So
yeah.
And I think there is a plastic bag tax up in Chicago now, is there not?
Very possibly. I know I have a kid who went to school in Northern California, and for a long time, you had to buy a bag if you wanted one. I know for years, Target has done, for every bag of your own that you bring, you get 5 cents off. So today I actually stopped by Target, brought my bags in. I brought 3 bags in, everything fit in one bag, and he still gave me 15 cents off for all of them. So, but it might need to be a little more dramatic than that. Or I think that making people pay extra for a bag might be one way. I had someone else who said they have the same experience. So we might just start a Twitter war on the people who keep giving us plastic utensils. So,
so we have more questions, Sam.
yeah,
So
I know.
okay, go ahead.
The before part of that is, do you have suggestions for how to incentivize? As you said, it costs it costs them money to use this kind of packaging. So is there a way that we can persuade companies not to, to reduce the amount of plastic before it gets to the consumer? What can we as consumers do to push for less plastic coming in?
Yeah, well, obviously not consuming it would slow it down. Use your purchasing power. That's a very powerful thing, right? If you don't buy these things, they're not gonna make them. Let me think about that some more. Can I come back to it again? Can you hit me with some other questions and
Yes,
take that idea around some more?
Yeah, so I have one that asks about the washer detergent sheets. Are you familiar with these?
Oh, yeah.
Yeah. What are those? Would you recommend those over using big plastic jugs of laundry detergent?
Oh, wait. Yeah. I thought you were talking about dryer sheets. So you're talking about packaging. It sounds to me like you're talking about.
Yeah.
No, there's laundry soap that comes in sheets.
Yeah.
Laundry soap that comes. She had like those little Tide Pods, those
Nope.
wrapped in plastic.
So they're plastic free, and I started at Jennifer. You might get these also here. I'm going to add you to the spotlight. I actually started getting these like 6 months ago, and they are sheets. They look like dryer sheets. The texture is different, and they are the detergent. You put it in your washer, and it foams up soap, right? It melts for it. And it doesn't seem to leave any residue.
Yeah, could be a water soluble polymer. I'm not familiar with the material. I have to get my hands on one and take it back to the lab.
Well, and related to that, just tips on washing. Another question was tips for washing so that we don't shed as much. I've read things like washing cold so do you have tips so that we as the consumers don't let our washing shed as many microfibers?
Well, it depends on the material. I just actually sat down and read a paper today it looked at polyester, it looked at acrylic, and acrylic was the worst, where they wash clothing multiple times, and then they did microscopy on the fibers. And you could see the acrylic was shedding really the fastest, the most abundant. And then I can't remember what this third one was. I'm sorry, it's been a really long day. But I believe that polyester, it showed that it really didn't shed as much as the other 2 materials. So it's a tough one, though. I see this thing about filters too. And you wash your filter, but then I always ask myself, was the filter made of?
Yeah.
And is that shedding microplastics? And then what do you do with the microplastics that get collected in the filter? You landfill.
Right. Yeah.
It's where do you put the stuff? So
right.
And one thing that, we probably have more questions on the laundry, but one thing that you had in a prior presentation that I walked around telling everybody I knew was how much worse for your health it is to drink out of a plastic water bottle.
Oh, yes.
And I went around to use that to convince people not to buy them.
Yes.
So can you tell us a little bit about that?
Oh, yeah. Your exposure from drinking from a plastic water bottle is incredibly higher than drinking from tap water. We know that water bottles are a major source, and even plastic cups. In fact, there was just a study that was released in Environmental Science and Technology. It was either Monday or it was late last week that showed, this is something like 90 trillion particles were released in a plastic cup that was heated to 70 degrees. And they were looking at nanoplastics. So they were getting down to really, really small sizes. It was incredible the amount of, and this was National Institute of Standards and Technology that published this paper. So they said, don't heat, the bottom line is don't heat up your plastic cup with water in it, right? I mean, you're better off using, glass or ceramic. You don't have anything to worry about there. Aluminum's a great material. I mean, it can be recycled indefinitely. But, honestly, there's a photo in my talk where we've actually looked at microplastics in aluminum can beverages, and we find them too, but nothing like a plastic bottle. We find a couple here and there, and we think it comes from the manufacturing process more than likely. But even that, there's a company that was making bottled water in aluminum cans. So they were down in Florida. I met them when I was at MIT giving a talk. But the only problem there is they had to coat the inside of the cup and the can with a polymer so it wouldn't influence the taste.
Right.
And I started to wonder, well, what was that polymer? What are we adding there? And what's going on with that? But it's hard to find perfect solutions. I mean, there's problems with every alternative you come up with. But the thing is, you don't want your alternative to be worse than the current problem, which is what we've seen a lot with chemicals, like PFAS, for instance. A lot of the alternatives that the chemical companies are coming up with are just as bad, if not worse, than the original materials they're intended to replace. But it's the game of regulation. We regulate the specific compounds of the chemical company. It makes a slight change to that chemical, and then we start chasing that one. And I guess it's job security for guys like me, but really, we're constantly in this cat and mouse game of.
Yeah.
But your data, and we've had some people put links in the chat of ways to voice your concerns to legislatures, to lawmakers about, reducing plastic, because I do think we need laws. But isn't that what some of your science lays the ground for? Whether it's me writing to Coca-Cola or McDonald's, or whether it's me writing to my lawmaker, that you've given me the science to bolster my ideas, right?
Absolutely. Oh, the science is out there, and it's not just me, it's the whole scientific community. I mean, there's so many publications on microplastics in the environment now and in our body. It's just overwhelming. I mean, I have to spend so much time just keeping up with it. But yes, absolutely. But the thing about it is, a lot of people say, well, there's no health effects. That they think that, sure, there's a lot of plastic and sure, it's in our body, but does it really cause any problems? And here again, that's why the big whole, most of half of my talk was that it's more than plastic. That we know that we add so much stuff to plastic. We know that there's, it's a lot more complicated than plastic alone. Yeah, you might feed virgin plastic to a bunch of fish and they seem fine, but that's not representative of the plastic we find in the environment. Does that make sense?
Yes. I will. I have somebody who's asking, a few minutes ago, you mentioned a recent report on plastic water bottles. And is that something that we can access, or is that a journal that people would need a subscription to be able to see?
You should be able to access it. And it's been Guardians has redone it. And the study was done by Sherry Mason. And there's been several of follow-up studies since. And if you can't find it, I have my contact in the presentation. Feel free to reach out to me. There was a great study done in British Columbia, or up somewhere in Canada, that looked at, what was reported for foods. They looked at salt, they looked at beer, why they had to ruin beer, but whiskey. They had to, they looked at all that, and then they took it and they compared it to what human consumption is, and they found that, people eat, I think that's where the quote came out, that people eat 5 grams of plastic every month or every week, or it's been a couple of years since I've looked at it, but you might have seen that one come up a lot in the headlines as well. But all that information's out there. And that's one of the things is people, I have a study where we're looking at microplastics in tap water in St. Louis. And really the kind of the goal of the study is to show that tap water is relatively safe, that people, don't need to drink bottled water. So that's kind of the goal of that project.
Yeah. We have someone who mentioned in chat that they worked on the bag tax in Chicago.
Mhm. Are they up at Shed Aquarium? Are they from Shed Aquarium?
No, it's, she's a legislature. I actually kind of said that, I mean, since that's not John's expertise,
Okay. We'll skip it for now.
let's skip around to some questions that we can get.
Thank you, Jordan.
Okay.
I appreciate it. Yeah.
I mean, like there's questions about the petroleum industry is focusing now on plastic production instead of fuel.
Yeah.
Okay, anything to add on that point?
No, I mean, they got to do something with it, right? Yeah, that scares me. Yeah. Isn't it, that it's just so crazy that these materials, I think single-use plastic is a major thing to tackle right off the bat. I mean, we should be addressing that right away. Isn't it crazy that here you have a material that you've designed it to last for hundreds of years, but it's only intended to be used for a couple minutes and thrown away? I mean, it's mind-boggling. It's insane. And I think that's a thing that needs to be tackled right away. And I do see a lot of cities and a lot of even state government is banning these things. Even if they're not allowing their organizations and municipalities to buy single-use plastics. So there is a lot of movement going on there.
And we had that pass in Lake County passed a rule for its own facilities that it wasn't going to buy single-use plastics. So
Sure.
we'd love to see that pass in more counties.
Sure. And you look at the Microbeads Free Act in 2014, it was effective. I mean, when Sherry was growing around the Great Lakes, I mean, all she was finding was microbeads. But now, no, most of what we find are little fragments,
Okay.
fibers.
And
So
I know we have experts on, I have one lady on the call that I know will correct me, but we have underground aquifers.
Yes.
So any studies that you can, that's where Barrington water, and we have people from all over on this call, but that's where Barrington gets its water. Do you have any studies on those or any?
Well, there is actually a group working in McHenry County, I think, I think when I was doing a talk for environmental defenders, that they told me that there was somebody from Northern and there was somebody from, I wanted to say US EPA or DNR, that was going to do some groundwater sampling in that region. Groundwater usually is pretty prone to be microplastic free because it's so deep in the ground. And a lot of times that water is 10,000 years old and such, and it's usually in confined layers. So it's hard for the microplastics to really get down that deep into the soil. But karst systems, that's a different story because those are open and very porous systems. So you would expect to find microplastics there, but in deep groundwater, I wouldn't really expect to find much. I would expect to find more from the pumping system and the pipes in your distribution system.
Interesting.
Or your softener.
All the more reason that nobody in the Barrington area needs to buy plastic water bottles.
Yeah. I do remember from a program I did on water safety a few years back is that we are all shallow aquifers in this area. So it is a concern. It's something to be aware of and to, and actually, I think you can see that video on the library's website still. You have to go way back in the YouTubes, probably 5 years back, but I think we still have that one up about the specific things that we find in the groundwater in this area and in the village and private wells.
Before we close, can John put his info back up, because it was up so quickly that a couple people messaged me that they still wanted to see his email?
Yeah.
Do you understand what I'm saying?
Yeah.
Yeah, I have a strange email address too. That was it for questions? Oh, you guys
Yeah, I'll have Sam check here, but
There's and I'll
Can you
share. Yeah.
I have a strange email address, but it's really me. Because there's too many John Scotts.
and people are sharing ideas in the chat and different
good.
solutions and things that are, it's worth everybody reading the different ideas that people have,
Yeah.
and some links to read.
Well, and what I can do as well, when I record something, it also gives me a transcript of the chat. So the folks who have provided links, I can pull those out and put them in the information that will be with the YouTube video.
Perfect.
You know, one of the things is, for instance, where I live in a real rural community and we don't have garbage service. And when you don't have garbage service, you really start to think twice about what you buy. So I challenge people, you know, pay attention to what you're throwing out. If you didn't have, if it wasn't so easy just to take that bag of garbage out to the trash, then you really start to think more about the things that you bring into your household. And I think that's important. It's just too easy to just take it to the trash. It's too inexpensive. But as landfills fill up and fill up and fill up, and this stuff does not degrade, that I think the cost of waste disposal will probably go up, and that'll be incentive for people to, you know, stop producing so much plastic waste.
One more question that popped up was that and I heard this when my children were little too, that, oh, you're going to use so much water if you use cloth diapers, that you're better off using disposable diapers.
Yeah,
but you would still, okay, you would still
disagree.
advocate for cloth ones?
Oh yeah, and I know people that have. Sorry, I don't have children, so I can imagine it's a pretty nasty job. But if I did, I would have no choice, because where am I going to do with all my plastic diapers when I don't have garbage disposal? I would have to wash them by hand. I would almost be forced to do it.
Yeah.
So, and I have friends that, you know, have used cloth, you know, and you know what? I mean, think about it. At one time, there wasn't plastic diapers around. I mean, my parents didn't, you know, I don't know if they used plastic or not, but their grandparents probably didn't. So we managed at one time without it. You know, give me convenience or give me death, right? I mean, that's, I don't know. Just amazing how long they live for.
Yeah. Yeah. Everybody potty train young.
Well, we sure appreciate all the work that you take. I mean, just so everybody knows, John not only does all this work to bring data that can bring about change, he also goes around speaking, you know, whenever asked, to help